So somebody has to start class with something they're happy about for today, because today was one of those days where Tom just wasn't very happy. I've had something from 7 o'clock this morning till now, and my favorite, though, was my wife telling me that it took 2 hours in the shuttle in New York City to get to the airport, and why was this guy stopping at all these stops? I pointed out that was his job. And so I put my family on a money diet, so that they'd start taking things like shuttles rather than Uber, and they'd start, drinking water instead of $6 coffees. You guys like that idea? I like that idea a lot. You know, what you save today, you can use tomorrow. Except we're all going to be dead anyway, so it doesn't matter. In the end, you may as well spend it. That's certainly my daughter and my wife's approach. So somebody else help me feel better about today. Mr. Bake, you got any good stories you want to share? We can come back to you if this is a challenge. We're talking about something happy. We'll talk about Klinkenberg later. Math ladies, anything happy today? Oh, you got something happy. This is the Walmart or what? What is Lake Walk? Ah. They let you in there without paying? Yeah, I've been there to the George, right? The Hotel George. Yeah. I got a lake at my place. You come hang out if you want. Lots of mosquitoes though. Anybody else got something happy? Mr. Desai, you always seem happy. I got an invitation to go to Rajiv Gandhi Institute today. What do you think? You like it there? Would you go instead of me? I felt awful, but I told this guy, I said, I'm just too busy. Give me a couple of years, and I'll feel like it. I did look it up. It seems like it's a nice place. Anybody else got any good news? Alex, we missed you last night, bud. Got any good news for us? Nothing. Nobody's got anything good? I'm coming to you last. Really? Okay, so my brain is really jumbled up. It's kind of like you took a Coca-Cola and shook it up and then put some electricity in it. So that's sort of how I am right now. But I was coming out of the office and I thought, I know I have a piece of rock that has a natural fracture in it, but I don't know where it is. So I looked through my rock box and it wasn't there. So somebody either stole it or I'm imagining things. But we'll talk in the abstract tonight about rocks with natural fractures in them. Is there anything else I can tell you before we really get into this? How many of you love all this math? This is really ugly, right? What are you most afraid of? Anybody want to confess? Cam? Cuddling? That sort of thing? Yeah. You're not going to tell us, are you? You're not going to tell us what you're afraid of? The dark? Wow. I can work with that. Mr. Bake, you're going to tell us what you're afraid of? Death? Yeah, we're all afraid of that. I was kind of hoping to be something like clowns, maybe. Gabe? Ants? Or migas? The little things that crawl around that you step on and you can kill 100 at a time? That bothers you? Really? Lightning? Yeah. Interesting. Mr. Desai, nothing? Things? Wow. Oh, lots of things. Little things. Like coins or snakes. Yeah. I don't know why people are so afraid of snakes. You know, my next door neighbor's kid, he reaches and grabs them and throws them around like this, and then bangs her head against a tree to kill him. And he's 7. But me, I see a snake and all I can think of is how he looks without his head. So that's me. Anybody else want to? Are you guys afraid of this? It looks ugly. Nah. So, they say you remember where you were when you did something. Well, when I derived this, I was in a hotel in New Orleans, and I was really bored. If you want to know the truth, I didn't really want to be there. So I needed to write this lecture, and I just took out their paper, and I kept trying and trying to figure out how they set this up. And finally, I reverse engineered it. This paper by Warren and Root is the start, at least in the Western literature, of the naturally fractured or dual porosity reservoir solutions. And it's actually pretty clever, reasonably simple, et cetera, et cetera. And were they the first ones to come up with it? No, they stole it from somebody else. They stole it from the Russians. I know it seems like it's always the other way around, but in this case, it's not. Barenblatt and Zeltov had published a paper on this, and I think that what Warren and Root did is they figured out how to make a connection condition, which unfortunately has a really bad name. It's called pseudo-steady state interporosity flow. It's not really pseudo-steady state, but the equation for flux is the same thing we use for pseudo-steady state. So the condition is that a molecule coming off the fracture face into the fracture follows a rule or follows an equation that looks like a pseudo-steady state material balance. Okay? It is not pseudo-steady state, but it looks like a pseudo-steady state equation. So what you're doing, and this is really simple, you have a differential equation for the fracture system, you have a differential equation for the matrix system. How do you marry them? Well, you could set them equal to each other, but that's not going to do any good. Because why? They have different pressures. The fracture system references the fracture pressure, the matrix system represents the matrix pressure. So you're going to have to connect them. How do you connect them? You're going to have an interface condition. And that's where Warren and Root came up with this idea of having a relationship, again, this material balance relationship for the matrix pressure, in other words, a flux out of the matrix, and then another equation that looks a lot like Darcy's law that couples a molecule, the behavior of a molecule of fluid coming off the fracture face into the fracture. So guess what connects everything together? Starts with L, next letter A, next letter P, next letter L, okay? It's the Laplace transform, okay? So when we take the Laplace transform of the differential equations, we get ordinary differential equations, which is fine. But more importantly, when we take the Laplace transform of these differential equations, they're first order differential equations for the interface condition, what happens? Something really wonderful. What's the Laplace transform of a first order ordinary differential equation? It's an algebraic expression. Okay? So it allows us to basically solve the algebra required for this, and then of course we set the equations equal to each other. Now, what pressure are we interested in for a naturally fractured reservoir? Are we interested in the matrix pressure or in the fracture pressure? Obviously the fracture pressure, because the fracture is connected to the wellbore. Okay? Any other questions before we start? So we'll derive all this tonight. And again, it looks, I started to say like Chinese, but that wouldn't be very nice. So I will say, after looking at Rajiv Gandhi University today, this looks like the Bangladesh language, right? See, I've been to Bangladesh, but I've never been to India. And it looks like they resolved all of those enclaves in India and Bangladesh, they removed them from the map, except for one. So I guess that takes time. So you guys are all friends now? A little bit? Okay. What's the difference between India and Bangladesh? Is it like Mexico and America? Or is it like Canada and America? You think so? Yeah, I'll mention that the next time I talk to a Canadian. So if that's true, what's the difference between India and Sri Lanka? Similar? Isn't it the same people? Okay, I'm teasing it out of them. They're not going to give it to me though. So I went to dinner at a Sri Lankan colleague's house one time, and he kept staring at me. And I was like, what? Is food or, something? I said, is there something wrong? And he goes, you do not look Sri Lankan. I said, what? And he said, you have a very famous Sri Lankan name. I was like, huh? You got it? It's Balsangami. One letter, a lot of difference. Okay? So Balsangami was the leader of the Tamil Tigers. You knew this, didn't you? Which was the terrorist organization. So I enjoyed dinner quite a bit after I figured all that out. Okay, so we have a couple of things that we're going to have to solve along the way. And one of them, or define along the way, one of them is the interporosity flow coefficient, and the other is the storativity ratio. When we create the dimensionless variables for this, we're going to have to couple the fracture permeability and matrix permeability into some sort of relationship. But more importantly, we're going to have to couple the fracture compressibility multiplied by the fracture porosity and the matrix compressibility multiplied by the matrix porosity. And it turns out that this expression falls out fairly naturally. Okay, so you'll see that as well. I know, just get on with it. Okay. And no more stories about Sri Lanka or India or anything else. I was very flattered by the invitation. Okay, so the first thing we'll talk about is what a naturally fractured reservoir looks like. As opposed to last night, we'll talk about what it looks like, and then we'll talk about how to derive it. Now, there are a lot of fractures that will look sort of like this. And, you'll intersect it with drilling. Have any of you seen cores with fractures like this in it that are not filled with cement? They may be filled with mud. So they say that these fractures are induced while drilling. That the action of the coring bit causes this. And like any good detective story, they say they can tell what happened because the fracture's full of mud, not full of cement. Okay? But you can also see filled fractures here. And then another one down here. Well, they may or may not be full of cement. We'll just leave that one alone. And the real key is, what's the distribution of fractures? Cam, any idea? How do we figure out the distribution of fractures? Before we really left shales or left sandstones and so forth and went to shales, there were a lot of people that were really trying to quantify fractures. Also, by the way, there was a recent well drilled in the Austin Chalk that was a monster. It was an oil well. And why is it a monster? Because chalk fractures. You guys can break chalk with your hands, right? So it's probably pretty fragile. Well, maybe you can't break a consolidated chalk, but you can imagine it's pretty easy to break. So what happens is you have these huge features where the chalk gets broken by some local geologic effect or tectonic effect, and it creates what's called a swarm of fractures. And obviously those are really good for fluid production. You also have features like down here, which are sort of a microfracture, maybe not microfracture is the wrong word for it, but it's a system of fractures caused by stress. Okay. Next is, how does rock actually fracture? And so if we take a piece of wood and you bend it, the top is in tension, the bottom is in compression. So if you're looking at a scenario like this, you can see stress cracks occur in the top, and then you can see these crushing effects occur in the bottom, and that's where these stress features occur, like these stylites that they're talking about, horizontal and vertical stylites. And then also sometimes you can have fractures which are transverse to the main. The main, in a situation like that where you're breaking it like this or where you're bending it like this, they will tend to break along this plane. But there may also be localized transverse fracturing as well. So when we have hydraulic fracturing, the real question is, what's the stress regime like? Now, everybody loves to talk about the Gulf Coast because there's so many wells, but what do you think, which way do you think a hydraulic fracture is going to propagate in the Gulf Coast area? Anybody? I'm going to take off my headphones, although I stepped on the wall. I'm going to walk over here and hopefully get some good markers. So the Gulf Coast region looks kind of like this. Here's Florida, blah, blah, blah. And what's the stress regime going to look like? Where's most of the stress going to be? Sorry? It's going to be towards the Gulf of Mexico. Okay. So how's rock going to fracture? It's perpendicular to least principal stress. So is it going to do something like this? Yes? No? Maybe? Or is it going to be more like this? What do you think? Well, it's going to depend on whatever it is in the region. Okay. Now the state of Louisiana, which is here, I drew it a little bigger than it really is. They had a rule that you had to drill wells north-south. And then you'd have a leftover pattern so you could drill one like that. And it turns out that the best fracturing orientation was north-south, just like that, because the hydraulic fractures occur like this. I'm not drawing this very well, but I think you understand. So what about this oddball well here? Well, sometimes it worked, sometimes it didn't, because this marker's shot. Here, Mr. Bake, put this in the trash so no one else will use it. I came close to putting it in the trash myself. Okay, so we'll just say that it's a regional issue, and you can see sort of how I've drawn it here, and that's how rock will fracture. So we need to think about, what kind of density of fractures there are. Do you think there's a lot of fractures, a few fractures? Are there big ones? How many of you have worked in well logging? Anybody? No? Okay. What's the tool that we use to estimate fractures? Do you remember? It's the FMI, the Formation Microscanner. Okay, and Schlumberger's is a resistivity tool. It creates an image of the borehole face. And what is Halliburton's? They can't have a resistivity tool because Schlumberger patented it. So what is theirs? It's a sonic tool. Okay, so they both generate an image. There are other tools as well. And what you'll see some sort of sine wave whenever you look at these things unwrapped, and that should be a fracture cutting through. Now, is the fracture conductive or not? We don't know. Now, I saw something really strange a few years ago. It was in the so-called Mississippi Lime. The formation was actually missing. It was gone. There was a hole about a foot wide. How do you think that well produced, class? It produced an ocean of water, like more than 10,000 barrels a day. It did produce oil for a couple of days, and then nothing but water. Okay. How do you fix something like that? I'm not joking. There was literally a cavern or a hole or something you're not going to overcome that. That's not a feature that's caused by this, but just for the sake of argument, it could be there. So we have the actual reservoir, and this is sort of what it looks like, given by Warren and Root on the left-hand side. This is probably the most famous picture of a dual porosity reservoir system in existence. The fracture is given by the broken black trend, and then we're going to represent it with the so-called sugar cube model. Are there alternatives to the sugar cube model? Of course there are. What are they? You can have slabs, you can have matchsticks, you can even have spheres, and I'm sure there's some other shapes as well. Does the shape really matter? It's got some influence. The slab is probably the one that's the most important, because the slab actually can be used to represent a quasi-dual permeability model, which we call transient interporosity flow. But for right now, we're going to assume is that we have some sort of a mathematical representation that looks like the object on the right, that there will be matrix blocks. All matrix blocks will be in contact with a fracture. Every molecule of fluid that comes out of the matrix block that will be produced has to go through a fracture system. Now, it's a little bit weird because we're also going to have a radial geometry here, but that's okay. We'll figure that out later on. But that's the conceptual idea behind the so-called Warren and Root model. And again, we're going to have an equation that models flux from the fracture face into the fracture, and we're also going to have an equation that models flux inside the matrix block, sort of a material balance equation. Okay. The next concept is, as I just mentioned, there's a low permeability part here and a high permeability part here. And the concept of this model is often called the Kazmi model, K-A-Z-E-M-I. Kazmi developed this when he had finished graduate school at University of Texas. He's currently a faculty member at Colorado School of Mines, and he had been at Marathon for about 25 years when he retired and went to work at Colorado School of Mines. He wrote a numerical model to simulate this behavior, and it was called sort of a layer cake model. This was a low permeability layer, and this was a high permeability layer, and you can repeat. You can have as many repetitive elements as you want. So this was derived by de Schwann. De Schwann is a Chilean masquerading as a Mexican. No, he was originally from Chile, and he was working at IMP in Mexico when he derived this model. Then another fellow by the name of Nahurieta came along, and he showed a little more practical approach than de Schwann's model. He showed how to solve it. And de Schwann, he has sort of the reputation as the father of the transient interporosity flow relationship, but Nahurieta was the one who made it practical. Nahurieta is an Argentine who was masquerading as a Mexican because he was working for IMP at the time, which is a Mexican Petroleum Institute. So these two guys are the reason we have the transient interporosity model. Now, there's been a lot of work since then, but for the sake of argument, those are the two that are important. These are the signatures in terms of the dimensionless pressure. Now, the way this works is the model starts, I'm going to bring the tools up, sorry. And what will happen is we'll have the initial behavior will be the fracture system. So this is a semi-log plot, so we have radial flow out of the fracture system initially. And then there's this huge transition region, and then there's flow out of the total system. Okay? So the part that you're really interested in is right here. Gabe, what controls this? Get it right, you go home a winner. Get it wrong, you stay the rest of your life. What controls that transition? Sorry? Thank you, Gabe. Now, let's try Gabe again. Gabe, what controls this feature? Okay, there's more to it than that. Thank you, Mr. Liu. Do you know what that is? It's the omega parameter. How much fluid is actually stored in there? So Mr. Liu is right. The interporosity flow coefficient determines the duration. But what determines the level of behavior? That'll be the storativity ratio. The storativity ratio is defined as this omega term, and the lambda parameter is here. So you have different omegas here, and I misspoke. This determines the length of the, well, it actually does determine the depth of the dip, because the more, the less, no, the less storativity you have, the worse this is. And I can show that by taking this curve, which is omega 10 to the minus 3, and I think it's this curve here. Sorry, I'm trying to do this way. Now, what happens if omega is equal to 1? Well, that just gives you the homogeneous reservoir solution. But if omega is a really small number, then there's a huge transition region, and you can see that derivative. What is this derivative trying to do, class? It's trying to go to 0. This is flat, right? What's the derivative of flat? 0. It's not exactly 0, but it's trying to go to 0. So the less storage here, the more this feature is going to be like this. Okay. So this is a semi-log plot, so it shows the radial flow in the fracture system, the radial flow in the total system, and then the transition flow. This is the derivative. Radial flow in the fracture system, radial flow in the total system, and the rest of this is this thing. Okay. What's the most important two-word question in the English language? Why? Is that like Hawaii? No, it's so what? Okay. So what? What does this mean in a practical sense? How many naturally fractured reservoir cases are you going to see in your career? A lot, a few, somewhere in between? Why are we studying this? I mean, it's a classic solution, so that's a good reason. But from a practical standpoint, how often are you going to see this in practice? Mr. Leo, you've had some experience with well test analysis, right? Have you ever seen a naturally fractured reservoir case in real life? No. There are a few in Africa. There's one in Venezuela or two in Venezuela. Maybe a few in the U.S. There's more than a few. Where are all the naturally fractured reservoirs, class? They're in the Middle East. Sorry? Correct. So they're all in the Middle East. Iran especially, right? Why Iran? The Zagros Mountains. They're an active stress area. So they've broken those reservoirs to smithereens. Also, you have it in Mexican offshore. Why do we have naturally fractured reservoirs in Mexico? Is that your final answer? Okay. You guys like when I go to Google? Not really. Come on, Google. Big Mexico asteroid. Right there, right? Let's do image. That's not what I was looking for. It's not seismic, but I know there's an image of it. Is this it? I mean, you can definitely see this thing. I'm trying to remember what kind of radar is it? Not what I was looking for. Definitely. Sonar. Okay, so there's where it is. I saw an image of it one time. Why are they showing submarines and seagulls and stuff? What's the name of this asteroid again? Anybody find it yet? Chicxulub. I can't even use copy here. It doesn't really mean anything. I'm trying to think of how this guy found it. I think this is what I'm looking for. Yeah. This is it. So it actually has, when they ran this device, whatever it was, they found this behavior. This is the Chicxulub. Yeah, yeah. So this pretty much shattered everything. So that's how that formed. Okay. You guys want to get hit by an asteroid? No, probably not. Okay. Nobody really worries about that. And these are the equations for that. We'll derive them. And these are some of the, we used derivative plots. And there were two kinds of derivative plots. One was Stewart and Ashurabi, or Ashur-Sabi. I said that wrong, pardon me. And it's the derivative and then dimensionless time multiplied by the dimensionless interporosity flow parameter divided by 4. And that sort of lined them all up. There's no storage on here. And then this is dimensionless pressure. And then instead of multiplying by 4, or sorry, dividing by 4, they divided by 1 over omega. It doesn't really change this, it just shifts it over, just FYI. And then the same thing for transient interporosity flow. We're not going to derive transient interporosity flow. But what do you notice the difference between transient interporosity flow and pseudo-steady state interporosity flow? What do you notice is the difference? What's the big difference? The transient interporosity flow starts at 0.5 and ends at 0.5, and in between it can have a minimum of 0.25. Okay, that's transient interporosity flow. On the other hand, we start at 0.5 for the pseudo-steady state interporosity flow, we end at 0.5 for the pseudo-steady state interporosity flow, and then God only knows what's going to happen here. Because if you have a low enough value of omega, it can just keep going down, down, down. And we were just talking about this. We're not analyzing anything. We're not deriving anything. But I wanted you to get a feel for how flexible this model is. What's the problem with flexible models, Mr. Desai? Okay, Mr. Brian, go ahead. Too many knobs to turn or too much flexibility? Can this model look like a fault? Yes. And in fact, this looks an awfully lot like a fault signature. The difference with a fault is this is at 1/2 and this is at 1. But if you're looking at data, you don't know the difference. You're looking at the shape. So Reynolds et al., when they wrote a paper, they said they were going to come back and explain how to differentiate it. They never did. But this could look like a single fault. It's not exactly the same because the fault signature is not this sharp over here. It takes a little more time for that to develop. What else could this look like? It could look like a radial composite system. What's your worst enemy in well test analysis? And this is why I got the invitation to go visit India, because this gentleman contacted me and was asking me for help on interpreting what? Variable wellbore storage effects in a data set. Now, first of all you have to do is say variable wellbore storage, and my brain starts to hurt already, because you can impose any model you want on the wellbore, and it will generate a signature that can be explained by something happening in the reservoir. Which means what? You think you're analyzing a reservoir signature, but you're actually analyzing a wellbore signature. Is that a good thing? No. Now, obviously, it isn't perfect, and obviously you would see this characteristic behavior. In the case of the data set that the gentleman sent me today, it had a hump. And a hump is a very, very indicative sign of phase segregation, a bubble rising up through the system. Nothing else produces that, except what? Could be a leak. A lot of people say that doesn't make sense. Well, whenever the signature hits a leak, or whenever the pressure distribution or the pressure behavior in the wellbore hits that point where it leaks, what's going to happen? The pressure is going to roll over, and that's exactly, it looks like a hump, but it's actually rolling over because there's a leak. There's not a lot of papers on leaks, I'll tell you that right now. In fact, the definitive paper on leaks was written by Ramey sort of as a homework problem. I had a case one time where I am 100% sure that the packer slipped. I'm not saying it failed, but I'm saying it slipped. And I knew why, because the tubing, actually, the stress on the tubing relaxed. So I think the packer slipped. What happened was a very high pressure well, and the well at the bottom, it was a very high pressure well, and we think that the packer released and then or reset itself or something. It slipped, and this on the data set just looked like nothing you've ever seen before. Kind of like a heart monitor, like that, and that is definitely not a reservoir effect. But something that's this complicated is probably going to get confused with something else. Again, it could be radial composite, it could be a fault, it could be a leak, it could be a wellbore storage effect. And I already told you that we're going to mix wellbore storage effects and naturally fractured reservoir effects. What do you think is going to happen when you do that? What's your worst nightmare? Is having so many variables that you can't see the signature anymore. And that's what's going to happen. Okay, we'll talk about that at the end. Next slide is where I made my student generate naturally fractured reservoir effects with wellbore storage. And all I really want you to get a feel for is this is a changing interporosity flow coefficient. So it's causing that. The only difference is each time he's changing that parameter, and you can see it moving through the system. Now, if you saw a data set that looked this complicated, and you didn't know that this was a naturally fractured reservoir, it could be a lot of things. Again, it could be a fault. It could be a changing wellbore storage effect. And that's why people, when they are trying to use software to figure out what something is, you have to think about what's the physical process going on here. I've seen people match pressure transient behavior with models that are completely inappropriate, such as using the naturally fractured reservoir model with wellbore storage to match a changing wellbore storage condition. It just so happens that the behavior conspires to match that. Okay, enough of that. Now let's talk about the solution. So this was all given in Warren and Root, not the steps, of course, but the guidance. This is their model. They start with the traditional diffusivity equation, And in this case, they write the diffusivity equation with a production term. You can see the fracture is producing and the matrix is injecting, so that's that. Now you can equate the two, doesn't really get you anywhere, but for some reason Warren and Root did it, so I did it. The next is the concept of what's the flow out of the matrix. And that looks exactly like what, class? Like the material balance equation. Okay? It is a material balance equation for the matrix block. So we're saying the porosity compressibility of the matrix multiplied by the pressure gradient of the matrix gives us the flux coming out of the matrix. Now, we have to have an interface condition that represents a pressure drop across the fracture face. And in this case, the rate is given by some constant which is unknown, the matrix permeability, the viscosity, the matrix pressure minus the fracture pressure. So this is the driving force. This is the momentum equation if you want to think about it. This is the material balance equation. This is a momentum equation. Everything else in this paper, everything else in this derivation hinges on equation 4 and 5. This is the so-called pseudo-steady state interporosity flow condition. It's not pseudo-steady state. It is a flow condition that models the behavior of a molecule of fluid from the matrix to the fracture. Probably the worst thing we ever did was give it the name pseudo-steady state interporosity flow. But for the sake of argument, it is an imposed condition. It is not pseudo-steady state of the entire system. So we set these equal to each other, as you would expect. We set 4 and 5 equal. And that tells us that the matrix pressure is equal to this constant, which we don't know, the matrix permeability, the viscosity, and then this porosity compressibility term, and then the difference between the matrix pressure and the fracture pressure. This is an absolute given that you want to use the Laplace transform on this. Why? What happens when you take the Laplace transform on the left-hand side, class? You're going to have U multiplied by the Laplace transform of PM. Okay? And what do you have on the right-hand side? You have PM minus PF, or I guess now PF minus PM. Okay? So now we'll take equation 4 and put it into equation 1, because why? We want to change everything to what? What's our goal? We want to have our equation written in terms of the fracture pressure. And we're going to, this is still in terms of matrix pressure, but we have this, we have that, and we're going to marry them all together. So without any proof, we define the dimensionless time as the permeability divided by the viscosity multiplied by the total, that is the sum of the fracture compressibility porosity plus the matrix compressibility porosity multiplied by RW squared. You remember where that came from, and then the whole system multiplied by T. So there's going to be some sort of relationship that pops up. You can see it. It's right here. There's that and there's that. So somewhere along the line in our algebraic manipulation, we're going to end up with having to marry those two. The dimensionless pressure relationship is the same as always. Of course, it's in terms of fracture permeability. So now we go ahead and we rearrange for time, and we rearrange for the matrix pressure, and we rearrange for the fracture pressure. We substitute all of these in the differential equation, and finally, when we're done, we have this expression for this is the interface condition. We have this parameter, which we still don't know. We have this relationship, the matrix permeability divided by the fracture permeability. We have a leftover RW squared, and now we have this. So that's starting to take shape, and then we have the difference between these. Okay, we're going ahead and define the interporosity flow coefficient as what's in front, and then we're going ahead and define the omega term in terms of this particular behavior, or if you want to rewrite it, it's equal to that. So we then substitute these definitions of lambda and 1 minus omega into equation 13. We have the partial derivative of the matrix dimensionless pressure with respect to dimensionless time. We have lambda divided by 1 minus omega, and then we have this difference. So we now have a condition where we have a derivative equal to some constants multiplied by a pressure difference again, this is a classic thing where we're going to use Laplace transform. So now we take those definitions of dimensionless pressure, dimensionless time, and other variables, and we substitute them into the differential equation, into the entire diffusivity equation. And when we're finally done, the whole thing works out to equation 19, but we're left with needing to define RD, so we're going ahead and define RD. And then when we're finally done, we have our traditional left-hand side, we have a right-hand side term, and then another right-hand side term. So what happens if omega is equal to 1? In equation 23, the final answer is what happens, I mean this is the final answer, but I'm asking you what happens if omega equals to 1? What happens to the system? Sorry? It becomes the homogeneous case. Okay? If omega equals 1, then this relationship becomes a homogeneous case. What two words do we say now? Thank God. Okay? Why? Because if not, we would have ended up with some really interesting non-uniform mess on our hands, but fortunately that worked out. So equation 23 is critical and equation 17 is critical. So do you guys know how we're going to marry these two? Because we have matrix pressure here and we have matrix pressure here and here. How are we going to marry these? Do I hear it? Okay, we're going to use the Laplace transform to marry them. Okay, so again, 17 and 33, they're our final relationships. Taking the Laplace transform of 17, we have U multiplied by the Laplace transform of the dimensionless pressure for the matrix. We have the dimensionless pressure for the matrix at time 0, which of course is 0. Then we have this multiplier, the Laplace transform of the fracture pressure, Laplace transform of the matrix pressure. Again, we set around and we solve the relationship for the matrix pressure in terms of these coefficients and that fracture pressure. Okay, that all makes sense. Now we take the Laplace transform of equation 23, and when we do that, of course, the same thing happens. The fracture pressure at 0, matrix pressure at 0 go away. We're left with a very nice little algebraic result here. And what do? We take this guy, 24, and we substitute him into 25. And when we do that, look what we have. We have all this ugly mess right here. So then when we do some algebraic manipulation on this, we have this, and our final form looks like this. So we're going to say that we're going to define f of u as equal to that multiplier on the right-hand side. So that's where that ugly thing came from. All this was a manipulation of that differential equation, the overall differential equation in the Laplace domain, and the dimensionless interface condition. So at this point, what's different, class? At this point, equation 28 is identical to the homogeneous equation, right? What happens to f of u if omega is equal to 1? Okay, f of u is 1 for omega equal to 1. So what happens? This whole thing reverts to the homogeneous solution, correct? So now, if you're paying attention, we're going to have to multiply through by RD squared again, just like we did before. And when we do that, what's going to happen? This was multiplied by RD squared. We have u f of u RD squared. So everywhere we had a u last time, we're going to have a u f of u, at least on the right-hand side. And so we do exactly the same thing we did before in the previous lecture. We work out all the algebra, and as before, this is our final form. Well, that is Bessel's modified differential equation. It's exactly given the same thing we did before, and it has this general solution. So we ended up with exactly the same differential equation as we did before. The only difference now is our substitution variable is u f of u rather than just u. And so we work out all the algebra and we come down to, where's our solution? It's simply this. We simply substitute u f of u everywhere we had u, except for the first term, and there's a story behind how that comes out. But everywhere else, it's u f of u. Now, one of the things you'll notice is that Thomson and Manrique and Gelmert, they derived the general relationship. This is valid for anything. So it's essentially a Laplace transform type function, but it's in u f of u. So you can use equation 43 for anything provided that f of u is known. So again, 44, 45, whatever, they're all, I guess I counted wrong here, but whatever, that's 44a. These equations are all the same as we derived in the previous night's lecture. The real important thing is where we end up. So we replace square root of u by square root of u f of u everywhere in the solution, where there's only one place for this case. And of course that's the definition of f of u. And we're more or less left with a final form. Now, we do want to take the log approximation, so we're going ahead and say that k0 is equal to 1/2 natural log 4 e to the 2 gamma 1 over x squared. And we substitute that into here. And this is our form for the moment. And you can see that we have 1 over 2u, natural log of some stuff, natural log of some stuff, because we can break this apart. And then we can have natural log of 1 over u, f of u. So we go on ahead and break it apart. Constant, not a constant, not a constant. Okay? So then we continue to separate. Oops, sorry, I went too fast. And we have log of f of u, and it can be written in a slightly different form, normalizing through in this fashion. And when we do that, we can write log f of u is equal to this. And when we do, we collect the whole mess, and this is our solution. So now your big question is, okay, what is the inverse Laplace transform of 1 over natural log of 1 over u, natural log of u? What is the inverse Laplace transform of 1 over u, natural log of 1 plus a multiplier times u, and then 1 over u, natural log of 1 plus another multiplier times u? Well, it turns out that this is pretty straightforward, because for 1 over u, natural log 1 over 1 plus u over a, that is simply EA of E1 of AT, which is very much similar to our original exponential integral solution. So we have that term, and then of course the inverse Laplace transform of 1 over u, natural log of u, is just the natural log of t plus Euler's constant. So when we come down and make the substitutions into 51 that are found in this table, we end up with, as expected, a constant. The transient flow solution, actually this whole thing is a transient flow solution for the total system. And then we have an E1 function here and an E1 function there. Now we can also take the derivative of these E1 functions, and that's what's over here. And the final form is going to look like this. So again, what happens every time we make omega equal to 1, class? What's going to happen? If omega is equal to 1 here, then that's going to be what? 0, infinite of minus, or sorry, exp of minus infinity is 0, exp of minus infinity is 0, and that's 0 times a half minus 0 times a half. That gives us back to the homogeneous solution. Same thing here for all of these cases where omega is equal to 1. These two are going to go away, and we'll be left with only the homogeneous part. I know this was a little bit fast and definitely boring, but you can get through this solution on your own. You can definitely do this. Now, the two-word question is, so what? So let's take a quick look at so what. This is just a summary of all the equations. Here's so what. There was a paper written in 1984 by Duprat et al. It was a Venezuelan limestone reservoir, not very many of those. And what you'll see is this well A17, this is actually a drawdown, so these data have a little bit of a changing wellbore storage coefficient here, but for the sake of argument, you do have transient interporosity flow. And then I also matched it with pseudo-steady state interporosity flow, so you can see a little bit of a ripple there. And then we come along to the buildup. So these are the drawdown data over here. Generally speaking, drawdown data are not as good as buildup data, so we'll see. Of course, this was 30-something years ago, 34 years ago. And you can see that the match using transient interporosity flow is pretty good here, actually throughout the whole way. Now, for those of you who are paying attention, this does actually look kind of like a fractured well in some ways, not exactly, but in some ways. And the same thing whenever we come down and use the pseudo-steady state interporosity flow. We don't get a very good match here, but we're okay over here. So it's kind of a combination of the wellbore storage and the naturally fractured reservoir model. Just for the sake of argument, how many of you want to build a better mousetrap? How many of you want to write your own pressure transient program or your own RTA or your own this or your own that? I hope all of you do, because I had another problem this week where somebody was generating results in one product and putting them into another product to see what the difference was. Well, comparing products like that is, what's that bottle you've got there? Pepsi. So that would be like drinking a Coke and then, spitting it back out and calling it Pepsi. That's a terrible analog, but, I'm trying to come up with something here so I get your brain thinking about this. If you're going to check software, checking it against another software is not really a proof, okay? And they were coming up with a discontinuity or something they couldn't resolve between the two. What's your first thought when somebody takes results from one program and puts it into another program and they don't get the same thing? What's your first thought? That is actually 0. That is correct. What's next? And it's along the same lines. Did they input everything into the second model exactly the same as they inputted in the first? And does the second model do the same thing that the first model does? And that caused me some concern, because the way they were trying to do this in Model A, they were generating a multi-well simulation. And in Model B, they were trying to interpret a multi-well simulation. Well, did they load everything correctly? Is that what the reason is? And I can't say. For one thing, I'm not going to go back and check it. But, the real question is, when you compare software packages, the best thing to do is check the analysis by hand, check the interpretations by hand. I've had 2 experiences in my life with software. One was not particularly, it was very educational, but it was not very much fun. And I think I mentioned that we wrote a competitor to the product by Kappa Engineering, or at the time there was another product called Pan System. And you know where the building is going up next to the Rise? We had an office in there, and just like you guys, we played like we knew what we were doing. And, every relationship is going to end, okay? This one ended pretty quick. And my partner was a really good programmer, but he wanted to be a billionaire, only he wanted to do it by himself. And let's just suffice it to say that as a software writer, I became a pretty good faculty member, and as a billionaire, he is a pretty happy consultant. But, we see each other now and then, and it's always good. If you're going to do something, you have to do it with a single passion. That's what Mr. Jose did with Kappa. He worked in freezing cold weather in the North Sea and scorching hot weather in the Middle East for flow patrol, wore the overalls, banged the hammer unions and everything else, and decided that wasn't a very good way to make a living. So he bought a Macintosh SE30 and began programming what became Kappa's software suite in a closet. And nobody bought it. Nobody even acknowledged it existed until he got a contract with Mobile, which doesn't exist anymore. But they put him on the map, and the rest is sort of history. I wish something like that could happen to you guys. But he lived on nothing. His office was a closet. Now he has offices all over the world. They've cornered the market, etc. But it was more out of other people getting out of the market or not keeping up with them than it was anything else. I'm not taking anything away from him. I also wrote a well testing package, and this is from, in addition to the one I wrote with the other fellow, I wrote my own well testing package, and this was it. It was called Piranha. I needed a fancy name. It was performance analysis, so I called it Piranha. It was never for sale. And then following that, in the mid 1990s, I needed to have a program to do RTA, so I wrote my own software to do that. Of course, I created it, so I knew what I was doing. And I was, if you're going to program your own code, you better be really good at it. How many of you taken Dr. Meridi's class? How many of you would like to go out and sell software? Yeah, that's what I thought. Okay. So the last, I think the last slide is another set of these. Yeah. There were some other wells from the paper from DePratt et al., and these data get a little wacky. This is very hard to match, class. Very, very hard to match. Now, Kappa has a tool, and so does John Spivey, where you actually grab the line and drag it. Computers are fast enough now to where you can grab the, or whatever you want to call it, you can calculate the behavior dynamically, and you can do that. My advice is not to use autoregression. On the lower plot and the upper corner, the lower left plot and the upper right plot, you'll see that there's more than one calculation of the derivative, and that's because this data was so bad that we needed to have a better inference of the derivative. So just FYI. Okay, that's the end of the the naturally fractured reservoir lecture. And I guess the story of the day is that this solution is not that bad. It's not that hard to not that difficult to derive, but it is extremely flexible. Please do not do the following. One of our first distance learning students was matching well test data from the Gulf of Mexico. The Gulf of Mexico has what? Anybody? They're usually very thick sands, very clean, very thick sands. And he was matching it with this model. And he was very proud of it. Very, very proud of it. What was probably going on after everything we've talked about tonight? It was definitely not dual porosity. It was probably a combination of, it could be high velocity, non-Darcy flow combined with wellbore storage. You can see one of the signatures over here in the upper right-hand corner. This is a very strong signature, and there are stronger ones than that where you actually have a much higher rollover feature for non-Darcy flow. So it could be a combination of things like that. But he defended, with every ounce of his life that a dual porosity reservoir model was correct. And we asked him repeatedly, what was the sand thickness? The sand thickness was the sand thickness was about 300 feet, and the permeability was a Darcy. You know what he was calculating from this from using the naturally fractured reservoir solution? What was the permeability he was estimating from that? Supposed to be 1 Darcy. What was he calculating? Think about it. This model allows much higher performance for the same permeability. 1 millidarcy. And he never stopped to think about it. The core data said 1,000 millidarcies. His history matching said 1. What would happen to you if you went to your boss with that kind of result? What do we call that? We call that a resume moment. Okay? You might want to have your resume ready to go. And he just never asked. There's geologists all around. They're like, termites everywhere you look, and they work all the time. Go talk to one. Ask them. They'll be glad to see you. But if you don't verify your geologic model, it's at your peril. I had another student who matched a bunch of well test data with a multi-layer model. All the properties of all the layers were the same. But he said, look, I use more layers. Must be better. What's this called? Yeah, I was doing that a lot. Okay, enough lecture for tonight.